Hi everybody! So now that we have learned about some vocabulary words that kind of apply to the first derivative, we're going to start talking about some vocabulary words that apply to the second derivative. So the first new word is point of inflection. Points of inflection are places where the second derivative equals 0 or the second derivative is undefined. So just like critical points, we're talking about where the first derivative is 0 or the first derivative is undefined. This is just the second derivative, but we're also looking for where it's 0 or undefined. However, that's not enough to make a critical point. To make a point of inflection. In order to be a point of inflection, you need to have the second derivative equal to 0 or undefined. But also, the second derivative needs to change signs at that value. If the second derivative is not going to change signs there, then it does not get to be a point of inflection. Now, unlike yesterday, where we had 3 options for finding critical points increasing and decreasing, here we only have 2 options. Either you have the equation of f of x, or you have the graph of f prime. So let's say you have the equation of f of x. Well, if I want to find the points of inflection, which I know are related to the second derivative, then first I'm going to find the second derivative. So if I take this equation, the first derivative would be 8x cubed minus 8x, and the second derivative would be 24x squared minus 8. Now again, I want my derivative to be equal to 0 or undefined. So in order to see where my derivative would be 0 or undefined, my second step would be to make that equation equal to 0 and solve it. In this case, I would factor out an 8, and I would get 3x squared minus 1. If I wanted to try to factor this remaining parentheses some more, it wouldn't work. So instead, I would solve that. I would have 3x squared minus 1 equals 0. If I add the 1, I get 3x squared equals 1. If I divide by 3, I get x squared equals 1/3. And if I square root, I get x equals plus or minus the square root of 1/3. As soon as I have those values, then I also need to think about, is my second derivative ever undefined? Because my derivative here is a polynomial, which means it doesn't have any corners or cusps or vertical tangents or anything like that, then we're never going to be undefined. So my final answer would just be x equals plus or minus the square root of 1/3. Now let's say instead of giving you the equation of a function, I give you the graph of f prime. Well, if I give you the graph of f prime and I'm asking you to talk about the second derivative would be the slope of f prime. So if I'm looking for the slope of f prime, f double prime will equal 0 at the maxes or the mins of this graph. So in this case, it would be here and here. Now I know those are not super clear numbers, so I'm just going to estimate that by saying 1/2 and -1/2. Now, so the second question I need to ask myself is the second derivative ever undefined? In this picture, I don't see any corners, any cusps, any vertical tangents, or anything like that. So my final answer would just be this guy. Now let's say instead of asking you for points of inflection, I ask you for concavity. To figure out if a function is concave up or concave down, a function is going to be concave up if the second derivative is greater than 0. A picture of what concave up looks like is like this. I usually say that it looks like a cup. A function is concave down if the second derivative is less than 0. I usually say it's down like a frown. So let's say I give you the function for f of x and I say where is it concave up and where is it concave down. First, you would find the second derivative. So the derivative would be 8x cubed minus 8x, and the second derivative would be 24x squared minus 8. We would make that equal to 0, just like we did in the other problem, which means we would have 8 times 3x squared minus 1 equals 0. And we saw just above here that that means x equals plus or minus the square root of 1/3. Now, in order to determine where I am concave up and where I am concave down, I need to look at the sign of the second derivative. So just like we made a table yesterday to look at increasing or decreasing, we're going to make a table here using these numbers to look at concave up and concave down. So here I would start at negative infinity. I would use the negative square root of 1/3, the positive square root of 1/3, and infinity. Now, unlike yesterday where we looked at what the sign was of the first derivative, here we're going to look at the sign of the second derivative. So if I pick a number that's less than negative square root of 1/3, some students are like, I don't know what that number is, and that's okay. We definitely know that negative 10 is less than that. If I plug that in, 8 is always positive. Negative 10 squared is positive 100. So 300 minus 1 is going to give me a positive number. I'm going to be concave up like a cup for that section of the graph. In between the negative square root of 1/3 and the positive square root of 1/3 is a number 0, which should be easy to figure out because one of these numbers is negative and one of them is positive. So if I plug in 0 to this function, remember we're always plugging it into the factored version, 0 times 3 is 0, minus 1 is negative, so this section of the graph is concave down like a frown. Last but not least, bigger than the square root of 1/3 would be like 10. 100 times 3 is 300, minus 1 is 299. It's positive, concave up, like a cup. If I wanted to list where my function is concave up or concave down, because of the way that this is defined with a greater than or a less than but no equal to, we always use parentheses around our intervals, so we're not going to include the endpoints. So concave up would be from negative infinity to the negative square root of 1/3, and then also from square root of 1/3 to infinity. Concave down would be negative square root of 1/3, comma, positive square root of 1/3. Now let's say instead of giving you the function f of x, I give you the graph of f prime. Since we want to talk about the second derivative is the slope of f prime. In other words, it's the slope of this graph. So we are going to be concave up whenever the slope is positive. So that would be from here to here and from here to here. So we would say from negative infinity to negative 1/2 and from 1/2 to infinity. Now we would be concave down when this slope was negative, so downhill. So I would be concave down in the middle of this graph, which would be from negative 1/2 to positive 1/2. Just sort of estimating those numbers because they're not clear. Usually they will be very clear where the maxes and mins are. So let's look at a couple examples. Here we're going to combine everything that we know so far. So I'm going to give you the graph and then I'm going to say find the critical points increasing, decreasing, which is all first derivative stuff. Then I'm also going to say find the points of inflection, concave up and concave down, which is all second derivative stuff. So here's how we could do that. Step 1 would be to find the first derivative, which would be negative 3x squared plus 6x. Then I would make that equal to 0. So step 2 would be to figure out where the critical points are, or in other words, where your derivative equals 0. If I factor out a negative 3x, I would get x minus 2 equals 0. So x would equal 0 or 2. In order to figure out where my graph is increasing or decreasing, I would make a chart. So I would start with negative infinity, 0, 2, and positive infinity. And then y prime would go in the chart. I would pick a number less than 0, like for example negative 1, and remember we're always going to plug these numbers into the factored version. Negative times negative is positive, negative 1 minus 2 is negative. Negative means I'm going downhill. Between 0 and 2, like positive 1, negative times a positive is negative. 1 minus 2 is negative. 2 negatives make a positive. Positive, I'm going uphill. Pick a number bigger than 2, like 10. Negative, positive, negative, when you multiply those together, downhill. So my increasing sections of the graph would be between 0 and 2, and my decreasing sections would be between negative infinity and 0, and between 2 and infinity. Next, we would look at points of inflection. Now, in order to do points of inflection, first, we would find the second derivative, which we can get by taking this guy's derivative. So that derivative would be negative 6x plus 6 equals 0. The reason we're making it equal to 0 is that we want to see where the points of inflection would be located. So step 2 would be solve that and make it equal to 0. I would factor out a negative 6 and I would have x minus 1. So I would just get x equals 1. And that would be my point of inflection. Now to figure out where my graph is concave up, concave down, etc., I would need to make a chart. So my chart here would start with negative infinity, and then I would have 1 and then positive infinity. If I pick a number less than 1, like 0, I'm going to have a negative times a negative, because remember we always plug this into the factored version, which is a positive, so I'm concave up. If I plug a number bigger than 1, like 10, I would have a negative times positive, which is negative, so I would be concave down, like a frown. Concave up then would be from negative infinity to 1. Concave down would be from 1 to infinity. Okay. And lastly, if I give you the graph of f prime, so this is the graph of the derivative already, and I say identify where the critical points are. We said that critical points were the same thing as x-intercepts, because those are the places where the derivative equals 0. So that would be at negative 4, 0, and 4. We said that increasing would be wherever the graph is above the x-axis, because this is already the derivative. So we're going to have a positive slope when we are above. So that would be here and here. So negative infinity to negative 4 and 0 to 4. We also said that decreasing was wherever the graph is below the x-axis, because that's where my slope would have been negative, since I have negative y values. So decreasing would be from negative 4 to 0 and from 4 to infinity. Now if we're talking about second derivative stuff, second derivative would be the slope of this function. So points of inflection are going to be maximum and minimum values. That's where the slope would be 0. So that would be here and here. And I would say x equals negative 2 and 2. Concave up would be wherever the graph is going uphill. So that would be between negative 2 and 2. Concave down would be wherever the graph is going downhill. That would be from negative infinity to negative 2 and from 2 to infinity. And we're done. All right, guys, thank you so much for hanging in there today and learning some stuff about second derivative vocabulary. I will see you tomorrow for some practice.